Hello, and welcome to reInvent 2020. My name is Sirirat Kongdi. I'm a Senior Solution Architect at AWS, serving the AWS worldwide public sector federal financial customers. In these sessions, I'm going to show you how to leverage AWS X-Ray to correlate the events, such as deployments, to help you understand the effect it has on performances and errors. First, I'll briefly explain what and why AWS X-Ray. We will go through a basic concept and terms in AWS X-Ray. Then we will dive deep on X-Ray console and learn how to use it to help you quickly identify the problem during the deployment. So let's get started. Millions of customers are using AWS Cloud today. They are trying to get the most out of the move to the cloud by embracing modern application development practices, such as moving toward the microservices architecture to achieve agility. They are building the distributed system and take advantages of AWS managed services, such as serverless service, which take away the heavy lifting task of managing servers. However, microservices and serverless architecture make observing application much more complicated. It is not enough to know that it's a problem in your application. But how do you isolate where in the distributed architecture that the problem is, especially when you introduce changes to your application? And one of the changes that you are supposed to be doing often is to support fast-moving business is a deployment. AWS X-Ray solves these problems. It's purpose-built for modern applications. X-Ray helps you understand where the root cause is of any problem. It tracks logs of all your ephemeral resources. You can follow the entire request path into the different layers and components of your application to figure out where the problems are. This is an externalization of what we do at Amazon. X-Ray is great for any microservices-based architecture, but it is particularly good for serverless application. So let's quickly review how AWS X-Ray works. First, you instrument each service in your distributed application using X-Ray SDK. The SDK records data about incoming and outgoing requests and sends it to X-Ray Daemon, which is a software running on your compute platform that runs your service. X-Ray Daemon then relays the data into X-Ray service, where the data is grouped and organized. Then you can view your application in the form of service map in the X-Ray console. You can use X-Ray Analytics to further deep dive and analyze issues. The data that is instrumented by X-Ray SDK at each compute resources is called segment. A segment provides a resource name such as host name and its IP addresses, details about the request such as user agent or client address, detail about the response such as status code or content, and issues that occur. A segment can break down the data about the work done into subsegments. Subsegments provide more granular timing information and detail about downstream calls that your application made, which can be a call to an AWS service, an external HTTP API, or database. You can even define arbitrary subsegment to instrument specific function or lines of code in your application. X-Ray aggregates the data from the subsegment into a single unit called trace. You can use this trace to follow the path of an individual request as it passes through each service or tier in your application. AWS X-Ray provides user-centric view of requests flowing through your application. So when you instrument your application, the X-Ray SDK records information about incoming and outgoing requests. You can add other information to segment document as annotation and metadata. Annotations and metadata are aggregated at a trace level and can be added to any segment or subsegment. Annotations are simply key value pairs that are indexed for use with filter expression. You use annotation to record data that you want to use to group traces in the console. Metadata are key value pairs with value of any type, including objects and lists, but they are not indexed. You use metadata to record data you want to store in the trace, but not needed for searching traces. To get started with X-Ray, you need X-Ray daemon running on your compute platform. For example, if you use EC2 instance, then you need to install X-Ray daemon. But if you want to use AWS Lambda, you enable tracing on the Lambda function. Then you use X-Ray SDK to further instrumentation. You can create subsegment, add annotation, metadata, and error information. AWS X-Ray SDK also provides instrumentation of downstream calls such as outgoing HTTP call, database queries, and calls to AWS services such as DynamoDB or S3. Now, it is a demo time. So for today's demonstration, I'm going to show you my distributed system, which is a simple API running on AWS Lambda with X-Ray SDK. I will show you how to use X-Ray Service Map and Analytics console to view and analyze these traces. I will show you how to put application information into traces and use them to help diving deep, especially when the change occurs, such as when you do the deployment. So let's talk about our application first. Our application is a simple web API built with API gateway with Lambda function. We will call it a receiver function. The receiver function calls another API to perform math calculation, so we will call it Calculator API. Calculator API is also built with API gateway and Lambda function. So now let's imagine that there are a bunch of devices out there with different type of devices and software version. And they all are making API call to our API to report their data. Now, let's take a look in the X-Ray console. This is Service Map, which shows the component that made up our application. Our application consists of API gateway, the receiver Lambda as the compute and the invocation, and the Lambda function code itself. The receiver function calls Calculator API, which also built with API gateway and Lambda function, and this made up the entire trace. Let's quickly analyze the trace using Analytics. Select API gateway and click Analyze Traces button, which brings us to Analytics console. Analytics console helps analyze trace data to see how the application performs. For our application, response time with distribution shows that the response time of majority of the traces are around 1 to 2 seconds. There are some there that are more than 4 seconds. Below the graph, metrics table shows the traces data grouped by request property, such as status code and HTTP method. It also shows the list of traces, which are the results of the filter. I can configure this metrics table to display annotations that I added to the segment. Let's change this metric table to by model. And this one by version. There are different types of devices. Phone made up around 39% of traces. Plate is about 26%. About 67% of all traces are from devices running client software version. Let's come back to response time distribution. I see the opportunity for improvement here to reduce the response time. Now I am interested in the traces with response time more than 4 seconds, and I can filter it here. Here we can see that all traces with long response time are all from unknown device type. So in the previous demo, we took a quick look into our distributed application in the form of service map, and we used X-Ray Analytics to understand the overall application performance and client behavior. We actually found an opportunity for improvement there. Now the device software team determined that they can improve the response time by making some changes to the device software. They are rolling out the software update version 10 over the air, and these devices are gradually updated. You now want to see how they are performing. So let's go back to the console and do the demo. We are back in the X-Ray console after we rolled out device software version 10. In Analytics, you see 50% of devices are upgraded to version 10 already. The response time of some of the traces are already improving to less than 1 second. Let's see what they are. I click and drag to select the traces. It automatically filters only the one with response time less than 1 second. And we can see majority of them are version 10. Let's remove the response time filter and focus on the metric table. In the metric table, by clicking the row, you automatically create a filter on the dataset. I click version 10 to filter the traces by version 10, which reflect in the filter in the trace set A in the blue line. I can compare version 10 with different version. I want to compare it with version 9. I added the traces set B with version 9, which shows in green. Definitely, response time in version 10 is shorter than version 9. I can compare with version 8 and the same thing here. Now I want to focus on version 10. I can also refine the dataset by clicking the refine at the filter there. Now Analytics only show the traces with version 10. Response time is much better now, but there are still those long response time there. Once again, let's filter them. And the unknown device still the problem. I can also drill down into the trace itself. Traces detail page shows all segments that make up the trace. You see the worker segment to 4.5 seconds. By choosing the worker segment, I can see the annotations that I used earlier in the metric table and the metadata. Now, I want to show you how to add annotation to the code, so you can use it to filter the traces. I use Serverless Application Model or SAM template to describe the receiver API. I need to make sure I set tracing to active for Lambda function and tracing enabled to true for API gateway. When you enable tracing for Lambda function, X-Ray automatically instrument the Lambda function invocation. But if you want further instrumentation, you need to use AWS SDK. This is the code for receiver function written in Node.js. We start by adding X-Ray SDK to the function code. I want to instrument the HTTPS call to the calculator API. So I enable HTTPS tracing by calling capture HTTPS global. For Lambda function, the main segment is immutable,
and controlled by the Lambda service. What you need to do is to add a new subsegment, add the annotation and metadata into the subsegment. I create a subsegment called worker to instrument the processing time and add annotations and metadata. I also create another subsegment called calling cal service to instrument the calculation process. Now we are back in the traces detail. In the receiver function, you can see the worker calling cal service and the HTTPS call to calculator API are shown as subsegments.
So by rolling out the device software update with the help of X-Ray annotation, we were able to verify exactly that the software version 10 has indeed improved the application response time. I showed you how to add annotation and metadata into the segment in the code to be able to use in X-Ray console. But we still found that there are still some devices that causing long response time. So this time, the application team is planning to release a new and improved version of Receiver API. And they are going to use Canary deployment. And they want to be able to track this release in the X-ray in the case that something bad happens. So let's take a look at how to achieve that.
In this new version of receiver function, I make an improvement to the categorize function to catch the bad result returning from calculator API, in this case negative value, and throw an error. Calculator API calculates velocity from the data that reported from the device. I use annotation to store the Lambda version using function version property from the context object. I am using serverless application model and code deploy integration to deploy receiver component using Canary deployment. Canary deployment helps reduce the risk of deploying new product by gradually sending the workload to the new version. Now, let's build and deploy the new receiver function. Now, the Canary deployment started. Let's go back to the console and see. After the deployment, we start seeing the errors appear in the service map. Red means fault, which is 500 series error, and yellow means error, which is 400 series error. It seems like the receiver function threw errors, causing API gateway to return 500 error to the client. So let's figure this thing out. Click API Gateway and choose Response Status of Fault to see fault traces. In Analytics, you can see error coming from the unknown device type currently. This could be a one-off or ongoing issue. Let's drill down to this trace. You can see the receiver function threw bad data. Final velocity cannot be a negative number. You can find exception stacks in the Exception tab. You can take a look at the annotation and metadata. Here you can see acceleration reported from the device is a negative number, which caused the calculator API to return a negative number and categorize function through the error. Let's come back to Analytics to take a look at our traces by removing the fault equal to true from the expression. Now we have our traces. Let's configure additional metric tables. Let's configure this metric table to group by receiver function version, and this one to status code. and this one to fault root cause. You can see from here too that the error is indeed bad data. Let's compare the new version, which is version 25 to version 24. In the time series, I can recognize the canary deployment. The deployment starts here, and there are two versions of Lambda function, 25 in blue and 24 in green, serving client requests. We are going to use deployment start time to compare the traces between and after deployment started. Now, remove filter from both trace sets. For trace set A, choose the time range before the deployment. Add compare box for the trace set B, remove filter, and select the range after the deployment started. You can see there are two 502 errors after the deployment. The delta for 502 is infinity as there were no errors before the deployment, while delta for 200 reduced by 0.5%. The metrics table grouped by the Lambda function version shows the traces for version 24 reduced by 13% since the deployment started, and canary deployment still in progress. It has been 3 hours now since the deployment. Let's compare traces between two versions again. The time series activities shows when the deployment completed. Now let's take a look at the traces before and after the deployment completed. The 502 error has increased since the deployment complete by 6%.
In this demo, I demonstrated how to enable X-ray and add additional information to the traces as annotation and metadata, which provide ability to deep dive to understand application behavior. I added device type, device software version, Lambda function version as annotations and used them to group and filter traces to help me very quickly understand the performance impact from rolling out the software updates. I added business data from application to the trace metadata, which helped me quickly identify the root cause without digging into the logs. I used X-Ray Analytics to compare performance and errors between trace sets, in this case, between software versions and also between before and after deployment. I used X-Ray Analytics to track down the issues and find the opportunity for improvement. So in the real life, your distributed system would be much more complex than my demo is. But hopefully this gives you some ideas of how to take advantages of X-ray capability to improve the ability to observe the behavior of your system. So if you like this session, then you might like this related session. So be sure to check them out. Again, my name is Sirirat Kongdi, and for today, thank you very much for watching and happy reInvent.